This is Math 251, and we're looking at section 11.6. For those of you who are wondering when we're going to get to the more traditional calculus topics, like derivatives and integrals, here we are. Finally, in this section, you're going to see those things. We're going to continue to work with these vector-valued functions that we introduced in 11.5, and in this section, we'll take a look at taking derivatives and integrals of those vector-valued functions. The good news is you probably already know how to do these, and you probably would do them correctly, even if we didn't give you any instructions. That said, I'm going to do a few examples. It may have been a little while since you've studied derivatives and integrals, so just to kind of help you review those processes, I've got a few examples here for us. The trick here is simply to treat each component as a separate function, and then use our normal rules to take derivatives. So if I want the derivative of this r of t, then r prime of t is simply going to be e to the negative 4t, and chain rule would give me times negative 4 there. Second component looks like I need a product rule, so I'll have the first t times the derivative of the second. Derivative of ln t is 1 over t, plus the second, ln t, times the derivative of the first, which is just 1, right? Just as a reminder, that's sometimes written as fg prime plus gf prime, right? Same thing. Last one, I probably want to think of this as 2/3 t to the negative first. So the derivative could be written then as negative 2/3 t to the negative second. And I'm not going to do a whole lot with these. I usually just kind of call this cleaning it up a little bit. I don't do a ton of algebra with my derivatives. I just kind of make them look a little bit prettier. So negative 4 e to the negative 4t, that's clearly 1 plus ln t. And I could write that as negative 2 over 3t squared if I wanted to, although I'm fine with the negative exponent as well. All right, let's do a couple more. This next one is kind of there to remind you of some similarities and differences with specifically the derivatives with trig functions. I would again like to do our prime of t. And this happens to be in the ijk form, so I'll write my answer in that same format. The derivative of sine t3 would be, sine 3t, would be cosine 3t times the 3 for the chain rule, and that's I. The j component, again the derivative of the sine function is the cosine function, with that same argument, t cubed. And my chain rule this time would give me a times 3t squared. And then remember here, we need to think of this as the whole function sine t to the third power. So when I do my power rule, I'm going to get 3 times sine t squared. And then the chain rule will give me a times cosine t. And that would be the k component. And again, I'm doing nothing here but just sort of cleaning things up a little bit. So 3 cos 3t I plus 3t squared cosine t cubed j plus 3 sine squared t cosine t. Okay. All right, what about part C? Each component here is a constant. So when I go to do the derivative, of course the derivative of any constant is 0. Or I could simply write that as the 0 vector. Sorry, little OCD here, gotta circle my last answer too. Notice, just like the derivative of a constant is 0, the derivative of a constant vector would be the 0 vector. All right, on the next page, I'm going to show you the derivative forms for the product rule in vector-valued function form. But I'm going to warn you ahead of time, they're true. I don't personally find them especially useful. Okay? You'll see they look just like they look for a regular product rule. If I want the derivative of a dot product, I can do u prime dot v plus u dot v prime, right? That's just like fg prime plus gf prime. Same idea. And the derivative of the cross product, u prime cross v plus u cross v prime. The only thing I might mention there is be careful with the order, right? We're used to being able to do things in any order. But with a cross product, if you ever use this rule, the order is important. Having said that, I'm going to tell you that, you all know doing a cross product is a little bit of a pain in the neck, right? So would I rather do the cross product once and then take the derivative? Or would I rather use a cross product rule where I actually have to do two separate cross products? Well, I'd rather just do it once in the first place and then take the derivative. And frankly, I usually do the same thing with the dot product. So these are mathematical theorems. They show you kind of the parallelisms between multivariable and single variable calculus. But in terms of how useful they are to us as derivative rules, I'm going to argue not really very useful. As you'll see when I do these next few problems, I typically just do the multiplication first and then take the derivative. So let's try that here in example 2. We want the derivative of e to the t times the vector v of t. And I'm just going to start by saying if I were to multiply v of t by e to the t, I have e to the t sine 2t, e to the t cosine 2t, 0. I've already done the multiplication. Now all I have to do is take the derivative. And I'm going to do the derivative by starting from here. So I do have a couple little product rules here. Let's see, I'd have e to the t times the derivative of sine t, which would be, sine 2t, cos 2t times 2, plus sine 2t times the derivative of e to the t, which is still e to the t. And the same sort of product rule here. I would have e to the t times the derivative of cosine 2t, which is negative sine 2t times 2 for the chain rule, plus the cosine of 2t times the derivative of e to the t, which is still e to the t. And of course the derivative of 0 is still 0. So I end up with 2e to the t cos 2t plus e to the t sine 2t. And second component, negative 2e to the t sine 2t plus e to the t cos 2t with 0 in the third component. Same basic idea with the dot product. I'm going to choose to do my dot product first. So I'm going to take the u vector, dot product with the v vector, which is going to give me 3t squared sine 2t plus 0 for the second component, plus 0 for the third component. Right? So the dot product actually turned out to be pretty simple this time, meaning that when I go to take the derivative of that dot product, again, I'm just going to start from here, and take the derivative of that. One more time, I've got a bit of a product rule here. 3t squared times the derivative of sine 2t, which would be cos 2t times 2, plus sine 2t times the derivative of 3t squared, which would be 6t, giving me 6t squared cos 2t plus 6t sine 2t. And notice again, the dot product of two vectors is a scalar, so not surprisingly, the derivative is also a scalar. All right, one more. Let's look at a cross product. This is the one where I really think that doing the cross product first is a big advantage. We don't want to have to do two cross products by trying to force ourselves to use the product rule. So I'm going to start out by saying, let's just do this cross product. And we'll do it the same way we always do. This may be the first time we've done a cross product with functions rather than just numbers, but the process is no different. I'll just rewrite my first two columns. And let's see. I'm going to get 0i plus t to the fourth sine 2t j plus 3t squared cos 2t k. Subtract. Looks like a 0k plus a t to the fourth cos 2ti plus a 0j. So my cross product is negative t to the fourth cos 2t is the x component, or I part. The j is going to be this t to the fourth sine 2t, just minus 0. And the k is going to be the 3t squared cos 2t, again minus 0. All right, I'm ready to do the derivative of my cross product. Simply by taking the derivative of my cross product that I've now worked all the way out. And notice it's a little bit of a pain in the neck. There's a few little product rules, but at this stage in our mathematical careers, we're not afraid of product rules, right? So let's see here. First component, negative t to the fourth times negative sine 2t times 2 plus cosine 2t times negative 4t cubed. And these are longer than they are difficult to do, so I'm going to start a new line here just to give myself some space. I would have, for the second component, t to the fourth times cosine 2t times 2 plus sine 2t times 4t cubed. And the last one, 3t squared times, oops, that should have been a negative sine 2t times 2 plus cosine 2t times 6t squared. 6t to the first. Goodness. My derivative skills must be a little rusty too here. All right, we're almost there. Let's go ahead and write this out. See, it's going to end up being a positive 2t to the fourth sine 2t and a negative 4t cubed cos 2t, and then a 2t to the fourth cos 2t plus 4t cubed sine 2t, and finally a negative 6t squared sine 2t plus 6t cos 2t. And it's a great big, not very attractive mess there, but there is the derivative of that cross product. All right, well, if you're not warmed back up on product rules by now, nothing will do it, right? So there's a bit of practice there. All right. The last thing that I want to do with derivatives is I'd like to talk a little bit about application. You may remember that one of the earliest applications that you did with derivatives in Calc 1 was to look at the derivative as the slope of the tangent line. Right? So if we just had a regular real-valued function, y is equal to f of x, then at this point A, if you had a tangent line, the slope of that tangent line was just the derivative, f prime, and actually I guess I should have put an f prime of a in there. It's just f prime evaluated at whatever that particular x value is at the point of tangency. We have a similar interpretation for the derivative of a vector-valued function. So if I've got a function r equals r of t, notice that I've got a curve now that's a directed curve because it's a vector function. And I'm looking at this point t equals a rather. If I take and draw not a whole tangent line, but just a tangent vector, the tangent vector will point along the same direction of motion as the original curve. So starting here at the point where t was equal to a, I'm going to sketch in a tangent vector. Okay. Again, it points this way because the curve was going that way. If my parameterization had gone the other way, I would have drawn the opposite tangent vector. Tangent vector points in the direction of motion. That vector, I'm going to call it v tangent because it is the tangent vector, is just the derivative r prime evaluated at a. So in functions of one variable, the derivative gave us the slope of the tangent line. In vector-valued functions, the derivative actually gives us the tangent vector. I'd like to just remind you of the types of problems that we did to find equations of tangent lines. I'm going to do the same problem twice, actually. I'm going to do it once here using the routine method that you learned in Calc 1, and then I'm going to go back and I'm going to do the same kind of problem using vector-valued functions. So if I want the equation of the tangent line to this graph, which is y is equal to the square root of x, at the point where x equals 1. So right there. What I would do is say that the derivative gives me the slope, right? Slope is equal to y prime, which for this function would be 1/2 x to the negative 1/2. And since I specifically want this at x equal 1, my slope just turns out to be 1/2. The point of tangency, we can see it clearly on the graph, but of course I could have also gotten it just by plugging the x equals 1 back into the original function. So the point is 1, 1. And then I would just get the equation of the tangent line using your favorite linear equation method, I like to go with y equals mx plus b, but if you like point slope form, feel free. I'm going to plug in my y is 1, m is a half, x is 1, and that allows me to solve for the b. Subtracting is going to give me a half for b. So this tangent line has equation y equals 1/2 x plus 1/2. And hopefully that looks at least somewhat familiar from your experience back from Calc 1. Okay. I'm now going to try and do the same problem, but instead of getting a function of one variable type of equation for the tangent line, instead I'm going to look at everything as vector valued functions, and I'm going to try and come up with a vector equation for the tangent line. So you see the same picture. Notice that the r of t here is simply a parameterization of this, right? If I let x equal t, then y would be the square root of t. So this is just the parameterization of my function that I was already using. And just like we were doing x equals 1 before, we're now going to do t equal 1. All right, so I'm going to start by saying, in order to get the equation of a line, instead of needing m and b, like I do when I'm dealing with y equals f of x form, I need a direction vector and I need a starting point. Right? So let's start by getting the direction vector. That's got to be the tangent vector. So we know that's going to be r prime. And the derivative of this would be 1, 1/2 t to the negative 1/2. And I want to plug in t equal 1. So that's just going to give me 1, 1/2. There's the direction vector for my line. I need a starting point. The point of tangency is t equal 1. So I'm going to want to use that as my starting point to make sure I start in the right spot. R of 1, 1 square root 1, or 1, 1. And then I just put together the equation of the line. I'm going to call this L of t for the tangent line, since r is already taken by our original function. And it's always t times that direction vector plus the starting point vector. Or t plus 1, 1/2 t plus 1. And again, that went through the starting point 1, 1. The direction vector said go over 1 and up 1/2. So that was my direction vector. But by adding additional copies of it, of course, I'll keep on going. I could add negative copies of it to get this side, and I end up getting the entire line. And actually, I shouldn't do that. It is a directed line, so it goes this way, just like the original graph also was directed. Like so. All right. So let's see here. We've got just a couple more examples to go, but this is getting a little bit lengthy, so we'll go ahead and pause right here, and we will come back and finish up our discussion of derivative vectors and what they tell us in the next video.